Hi, Peter. Can you listen to us?
Oh, yes, I can hear you. I can hear several people actually. Can you hear me?
Yeah, we hear you fine.
There is some echo though when you speak, it seems.
Yeah. Okay.
I suppose maybe there are two computers open at your end, or but anyway, I can hear you and you can hear me.
I think there. I think that's it. It's fixed now.
Yeah, I think it sounds better now.
Okay. Bueno, vamos a empezar el congreso el día de hoy. Thank you, Peter, so much for being here with us. Eh, I'm going to present you in Spanish first, and then you can start your presentation that you have for us today.
Yes.
I'm just going to stop sharing. Well, no, after that. Bueno, buenos días a todos. Vamos a comenzar el quinto y último día de nuestro Congreso Estudiantil de Matemática y Física. Y para hoy tenemos a un gran ponente que se llama Peter Larsen, ¿verdad? Peter actualmente ocupa la posición de coordinador senior científico y de comunicación en el Cosmic Dawn Center en Copenhague desde 2020. Antes de asumir este rol, entre 2016 y 2020, Peter se desempeñó como investigador postdoctoral en el Institute for Theoretical Astrophysics en Oslo. En los años 2015 y 2016, Peter dedicó sus habilidades como administrador de sistemas, soporte de IT en el Dark Cosmology Center en Copenhague, antes de lo cual llevó a cabo su investigación postdoctoral en DART 2012 a 2015. La destacada trayectoria de Peter incluye varios logros notables. En 2021 fue reconocido como el autor del artículo de noticias de investigación más leído en la Universidad de Copenhague. En 2019 recibió el reconocimiento como el mejor autor danés en divulgación científica del año 2018, gracias a su artículo Big Bang, an Eyewitness Account. Este logro se destacó en un periódico de Dinamarca, la Fundación Danesa de Investigación Nacional, y el artículo está disponible en danés, inglés y noruego. En 2011, Peter alcanzó la posición de primer autor del artículo más citado en astrofísica en Suecia, y la combinación de su experiencia científica y habilidades de comunicación lo convierte en un orador destacado y valioso para la opinión científica y el público en general. So, Peter, when you're ready, you can start your presentation. We're just going to stop here the stream.
Thank you very much for the introduction. I understood some, and I think I understood the gist of it. Thank you very much, and thanks for giving me this opportunity to speak for you. Before we start, I just can you remind me how long it should be? I think Pedro said 50 minutes. I just wanted to make sure that's correct. Are you still here, Pablo? Okay. I'm hoping so. So anyway, thank you very much. I'm as Pablo said, I'm doing a lot of science communication, but I'm also an astrophysicist. And thank you. Yes, 50 minutes. And my research concentrates about one specific emission line, and as I understand, you are not, well, maybe some of you are astrophysicists, but most are either physicists or mathematicians. So I would like to talk to you about this specific emission line that I'm researching, but it's going to be very slow. And yeah, if you have questions on the way, you're welcome to interrupt. But otherwise, we can also take questions at the end. So this emission line that I'm talking about is called Lyman alpha, and in 50 minutes you will share my passion for this line, I'm sure. So let me share my screen. Let me see. Okay, I'm a bit in doubt whether you can actually see the correct screen. Maybe I'm actually, to make sure that we are on the right screen, let me do like this. Right. Sorry for this. Yes. So this emission line, as I said, is it's called Lyman alpha. And
yes, we can see your presentation.
Perfect. Thank you. Thank you very much. Maybe I should just say, so I heard that you already said that I'm from the Cosmic Dawn Center, but yeah, so we are a small research center under the Niels Bohr Institute, where we do research in galaxies and mostly observational, but a few theorists as well, and I'm one of those. And we are interested in galaxies, and a galaxy is what you see here, a huge collection of stars. Maybe I don't know if you also see me, but actually it's the same galaxy that is behind on a poster behind me. It's a very beautiful one. But galaxies look in many different ways, and we want to know all we can about these galaxies. And a particularly good way to study galaxies is through an emission line called Lyman alpha. It's the Lyman alpha is the name of this photon with a specific wavelength coming from hydrogen, and it's the most common photon coming from hydrogen, and hydrogen is the most common element in the universe. So in many cases, especially when galaxies are forming, Lyman alpha is a very prominent emission line. But it comes with a price, because it turns out that it is compared to other emission lines, it's quite difficult to interpret, and I will explain why. So this is a very beautiful galaxy. The galaxies that we study usually don't look like this. They look more like this, like little blobs, very small because they're very far away, because we're interested in the early galaxies in the early universe. So that means that we have to look very far into the distant universe. So usually we don't have all these details that you saw in the previous picture. We just have a little blob of gas and hopefully also a spectrum. And then we have to extract so much information we can as possible. So what is Lyman alpha? Yeah, okay. I will just an overview. I will talk about what is Lyman alpha, and then show you some theoretical results. I'm a theorist. But also some observational results in the end, because I'm working with observers, I guess it's called. So what is Lyman alpha? Lyman alpha is, so this is a hydrogen atom. You have the proton in center and the electron in the ground state, and then you have other states. And if the electron is in the first excited states, so it's excited, it's we can illustrate this by its jittering back and forth. Then at some point, it will fall down to the ground state and emit a photon, and that photon is called Lyman alpha. It has a specific energy corresponding to the energy difference between the first excited state and the ground state. And it also has a specific wavelength, namely, so astronomers usually measure wavelengths of this kind of light in angstrom, which is a tenth of a nanometer. So the Lyman alpha wavelength is 1216 angstrom, which is like 122 nanometers. So to create Lyman alpha, we need an electron in the first excited state. And how can we get it there? So there are two different ways to get the electron up. One is by first ionizing a neutral hydrogen atom, like this. You have an energetic photon coming in, knocking off the electron. And then at a later point in the life of this hydrogen atom, we have electrons coming around. Suddenly, one electron comes down, and let's say it ends up in the first excited state. In that process, it emits a lower energy photon. And then we have the electron where we want it, and it will fall down and emit a Lyman alpha photon. So that's one way to create Lyman alpha. The other way is through collisions. So I should say, it turns out that for each ionizing photon that ionizes, so a photon that ionizes a hydrogen, then when you have the recombination, an electron coming back, it can end up here and emit a photon with a specific wavelength. It could end up here, or it could end up here, or whatever. So, and it's not always that it will result in a Lyman alpha photons, but for each ionizing photons, in 2/3 of the cases, the result is a Lyman alpha photon and then some lower energy photons. The other way is through collisions. So you have a neutral hydrogen atom in the ground state and a fast-moving electron up here, like this. Bow. And the energy, the kinetic energy of these particles goes into putting the electron in the first excited state. And so you lose kinetic energy, and the particles therefore continue with a lower speed, and then later a Lyman alpha photon is emitted. And when I say later, it's very fast. It's of the order of 10⁻⁸ seconds. So what happened here is that we had two fast-moving particles that collided and then converted the kinetic energy into photons. And that so what happened is actually that the gas has cooled. So we also call this cooling radiation. And this is a very important mechanism in galaxy formation, because galaxies form by gas collapsing, huge gas clouds that collapse. But when the gas collapses, it heats up. You know, when you compress a gas, it heats. And if it heats too much, you cannot compress it more because the energy of the particles is too big. So you need some process to make the gas able to cool. And this is one of the processes. So that's why it's also called cooling radiation. So these are the two mechanisms. When stars form, they form inside dense clouds of gas and dust. And you have the densest parts collapsing into stars. And then you have a population of stars that starts to ionize bubbles of ionized gas inside the clouds, and they will disperse the clouds, so the clouds will dissolve. And then the biggest of these stars, the so-called O stars and B stars, they emit lots of ionizing photons. They're very hot, much hotter than the sun, 40,000 Kelvin maybe, or 30,000 Kelvin. So they ionize the gas in the inner part of this this region. And then when you, as I said before, you ionize the gas, then it recombines because it's very dense. So the recombinations happen fast. And then for each of these ionizing photons, 2/3 Lyman alpha photons. So for each 3 photons, you have 2 Lyman alpha photons, which can then escape. So you convert a lot of ionizing photons to Lyman alpha photons. And this was actually predicted in this paper that I show on the right in 1967. The paper is published in 1967 by these two guys. And this is a very important paper in the galaxy formation, where on page 877, they show a spectrum of a hot star here. And all the photons that are able to ionize the gas is used and 2/3 of them produce a Lyman alpha line. So what you do here is to take a huge part of the spectrum and convert into a single emission line, Lyman alpha. And that makes the Lyman alpha line extremely bright in principle. So these guys, so at this time in the 60s, galaxies were only known in the rather local universe, but they predicted that we should be able to observe the distant galaxies if we looked for Lyman alpha. And that's nice, but the observers did not confirm this. So people were thinking maybe this is wrong or something. What can explain this? For several decades, actually, so such galaxies were not observed. So let me see. I just need to take care of the time. Yes. Okay. I just repeat the two mechanisms. One is ionization and recombination, and this is mostly by stars inside the galaxy, but actually there's also a UV background between the galaxies that can ionize the gas in the outskirts of the galaxies, and this can also produce Lyman alpha. And then the other process is collisions, which gives cooling. And these are the two equations that show you how much energy you get out of the two processes. The ionization and recombination, the energy emitted here depends on the density of electrons and ionized the ionized hydrogen, which is just a proton, because these two need to recombine. The collision, there you have a neutral hydrogen, so this is the neutral hydrogen density and the electron density, and then these are some quantum mechanical factors. So you see that you have here the efficiency of these processes as a function of temperature, and the recombination decreases with temperature, because if the gas is too hot, then the particles cannot recombine. They are simply too hot, and they will just collide and leave each other again. The collisions are more efficient when the temperature is higher. If the temperature is too low, then the collisions are not energetic enough to excite the electron. But if the temperature is too high, then you don't have the neutral atoms. So there's some sweet spot around 10⁴ Kelvin where Lyman alpha is emitted most efficiently. So radiative transfer is the theory of how light propagates in a medium. And for normal light, it's usually quite simple. You have some photons emitted, and then some fraction of it is absorbed in the gas before it reaches the observer. For Lyman alpha, it's much more complicated. So, as I said, the energy of a Lyman alpha photon corresponds to the energy difference between the ground state and the first excited state. And that means that if a Lyman alpha photon meets a neutral atom, then it excites, then the energy corresponds exactly to this difference, and it can excite the electron, and then the electron can de-excite and emit the Lyman alpha photon, but in another direction. So actually, the photons are not absorbed; they are scattered, as we call it. So it continues, but in another direction, and this makes it extremely complicated. So if what you have here is a lot of atoms shielding a star, and then you have a Lyman alpha photon, and it will scatter, make a random walk before it reaches the observer. So one of the reasons that the people in the 60s and 70s and even the 80s did not see the galaxies is that if you have just a little dust, interstellar dust, mixed between the gas, then because the way for the Lyman alpha photon to exit these gas clouds is very long, much longer than a normal photon, because it's increased tremendously. Then it doesn't take very much dust before it can, the probability of being absorbed by dust is much higher for Lyman alpha. So this was one reason that people didn't see it, or at least one of the reasons they could think of. But it turned out also that the telescopes at that time were simply not big enough. So eventually in the 90s, when the telescopes got big enough, the galaxies were indeed found, Lyman alpha galaxies. So this is the line profile of the cross section of a hydrogen atom as seen from for a Lyman alpha photon. So it's basically it looks like a Dirac function, but it's called a Lorentzian function. So if we zoom in here, zoom in a lot, then you can see it has some width, but it's really, I mean, the photon energy has to be extremely close to 1215.67 angstrom. The width of this line is actually related to the Heisenberg uncertainty principle. The lifetime that the electron is excited, and the energy width of this line is of the order of the Planck constant. So if a photon has an energy which is just a little too low or a little too high, then it cannot be absorbed by so the photon can just pass right through the atom. However, this is if the atom is lying perfectly still. If you think of a photon which has a little too high energy, so it should not be able to be absorbed by the hydrogen atom. But if then the atom is moving away from the source, then in the reference frame of the atom, there is a Doppler shift. So the photon is seen as a lower energy photon. So with the right velocity of the atom, then suddenly the photon which was had a little too high energy, it will actually have the perfect energy. And this effect will tend to broaden the line, because when a Lyman alpha photon enters a clump of gas, then the gas particles are moving with all sorts of velocities, like the thermal velocity. And that effectively broadens the line. So you see, when you increase the temperature, then the line can actually be very broad, the line profile. And if we look at it on a logarithmic scale, then you can see that in the very center of the line, the line profile is dominated by the motion of the particles, the thermal motions. But in the wing, you have the part from this Lorentzian natural line profile. This is maybe a bit complicated, but I will illustrate now. So the total line profile is a convolution between these two different processes. So you see here, this is a Lyman alpha photon, but a Lyman alpha photon which has a little too high energy. So it comes in, but it just passes straight through. But now let's say that the atom is moving away. Then in the reference frame of the atom, the too energetic photon is redshifted a little, so it becomes a true Lyman alpha photon, so to speak. Then the atom continues, and then the electron is de-excited. If now the photon, the Lyman alpha photon, is emitted in the opposite direction, then it is redshifted because it's emitted from an atom which is moving away. And that means that a photon that had a little too high energy is scattered. And then if it's scattered back to the direction where it comes from, it now has a little too low energy. So what happens here is that the photons are scattered and diffuse in space, but also in frequency. They change the frequency for each of these millions of scatterings that they perform. They will change the frequency a little back and forth. And this, this is what makes it really complicated. So you see here, you have the source, but now you have atoms that are moving. So for each scattering, you have a Doppler movement. And then if the photon is in the end scattered to a very high frequency or a very low frequency, then suddenly it can escape, because now the atoms are no longer able to absorb them. This can be calculated analytically for some very simple cases only, and this was done in the 90s mostly. So you can imagine a slab of a gas that is at the same temperature and is homogeneous, so no clumps or anything, and you just have a source in the center. or you can imagine a sphere of gas. So very simple configurations of gas. And then you can actually calculate that this is how the spectrum of a Lyman alpha source would look, because you emit photons here in the line center, but here the opacity is very high. The opacity of the gas is very high. So they change the frequency for each scattering, and eventually when they have scattered and changed their frequency either to lower frequency or lower wavelength, so higher frequency, or lower frequency, only then can they escape. So this is a characteristic spectrum of a Lyman alpha source. It has these two double profiles. The exact shape or the exact separation of these two peaks depends on two factors, namely how many atoms there are, because more atoms means that they have to scatter more, and how hot the gas is, because the faster the gas the particles move, the bigger the Doppler shift the photon get for each scattering. So in this case, we have column density. That means so the column density is 10 to the 19. That means that you will meet 10 to the 19 atoms on the way out, basically. And the temperature is 10 to the 3 Kelvin. If we increase the column density, what I mean is more atoms, then the peaks are separated even more. The photons simply have to scatter to even higher or even lower energies before they're able to escape. Otherwise, the gas is simply too opaque. But so more atoms give larger peak separations, but higher temperature also gives larger peak separations. So we can see if we increase the temperature, the same thing happens. And in fact, unfortunately, there's a degeneracy. So you see, you get the same result for two. Here's an error. The temperature are different, but the column density is also different. So here it should say 19 instead. The point is that you can have different temperatures, different column densities of gas, and get the same result. But usually gas that is able to scatter Lyman alpha photons is of the order of 10 to the 4 Kelvin, because if it gets hotter, then most of the atoms will be ionized. So you can assume sometimes that it's only 10 to the 4, and then you can actually see, if you see a spectrum, then you can get an idea of how many atoms are there. In real galaxies, it turns out that sorry. In real galaxies, it turns out that gas is very often being expelled from the galaxies, especially if you have galaxies that are highly star forming, because the star formation pushes the gas, both because of the radiation pressure, but also because the gas is heated. So and when the supernovae explode, they also create these huge bubbles that can expel the gas out of the galaxies, so out in the intergalactic medium. And when you have atoms that are all moving away from the center of the galaxies, then in the reference frame of an atom, the photon will be redshifted. So that means that if a photon is a little too energetic, then it can be scattered. If it's a little too little, it has too little energy, then in the reference frame of the atom, it will have even less energy because the atom is moving away. So photons that are too red, so to speak, so have a larger wavelength than the exact 1215.67. They in the reference frame of the atoms, they seem even redder. So they will see a gas that is very transparent and they can escape. The photons that are too energetic, they will actually, in the reference frame of the atoms, they will be seen as being in the line center, so they will scatter. So this means that when you have outflowing gas, all the blue photons, like the energetic photons, it's difficult for them to escape, and they will eventually scatter and become redder and redder, and that means that the gas is not able to escape before it's being redshifted. So these two peaks will actually be converted into one peak, the red peak. And when we observe Lyman alpha galaxies, the spectrum actually usually only has one peak, namely the red one, because you often have outflows in galaxies. Let me see. So, as I said, analytical solutions only exist in very few cases. So people in the beginning of the 60s already predicted that computers were needed. And this is, there was a paper by this Osterbrock where he talked about computers. And this is this picture that I'm showing here is the first computer in my country, Denmark. It had, I think it was able to do 15,000 calculations per second, which is a lot more than a human being, at least. But it's of course completely minuscule compared to today, where they are modern computers are measured in teraflops. I mean, like trillions of operations per second. But it's a start. So this is what I've been doing a lot, making computer simulations of Lyman alpha photons. And the best approach to this, because you cannot do it analytically, but you can do so-called Monte Carlo simulations. And Monte Carlo refers to the famous casinos in Monte Carlo where you gamble and you roll dice. And the reason is that, so what you do is you have a random number generator that you use to give you get random numbers. So you start by emitting one Lyman alpha photon in a random direction. So you draw a random number. And then this photon is propagated through the interstellar medium, ISM. And then at some point, it will meet either a gas particle, a dust particle. And if it's a gas particle, then it will be scattered in a new direction, and it will, depending on which direction and depending on the speed of that atom, it also changes its wavelength. And then you propagate it in a new direction and interact again with the particle and in new direction and so on. And then you follow that photon, and then maybe at some point it meets a dust particle, and the dust particle has some, it's called albedo. So it can either scatter the photon actually, and you get a new direction, or it can, and then you continue, or it can absorb it, and then the photon is gone. And then at some point, if it's gone, you emit a new photon. And at some point, the photon, if it's not absorbed by dust, it will escape the galaxy. And then you have emitted one photon from the galaxy with one specific direction and one specific wavelength. And then you do that again and again and again and again, and do it for many photons, maybe 1 million photons. And then eventually you have enough statistics that you actually can get an image and a spectrum of the galaxy. So this is how such simulations work. Right. So sorry. And then after escape, you emit a new photon, and then eventually you get a spectrum like the ones I showed you before, these double peak spectrum, if you emit it from a sphere of gas, for instance. So in the beginning, when people started doing such simulations, computers were so slow that, I mean, you could basically only confirm the analytical simulations that already were available. But then eventually computers got better. And that's good, because galaxies don't look like this, right? Galaxies look like this, I already showed you, or this, or this, or even this. And this is what we would like to see. How would this how can we calculate the emergent spectrum and image of Lyman alpha from such galaxies? And the approach that I've taken is to do basically the same as emitting photons in a sphere, but just a little cube. And this little cube is then characterized by some density. It's the same density all over, and some temperature, and also some velocity. All the gas particles have their individual velocities, but they also move maybe with some collective velocity in some direction. And then you emit a photon and follow it as it scatters around until it escapes this cell of gas. Then it can enter another cell, which has another temperature and with atoms with another velocity and another density. In this case, let's say it's more dense, so it scatters more. And then it exits this cell and it goes into another cell where it's less dense, and so on. And you can build up more cells and follow the photons as it scatters around. And in this way, you can build up something that looks like a galaxy. All you need is enough cells. And what you can see also that the cells don't have to have the same size. They can have, if you have a very dense region, you can subdivide each cell into 8 cells, and those cells can be divided even further, and so on. So you can continue and continue, and then eventually, and here, let's say here's also some high density here, and then eventually, so the photon exits this box of cells, and in this way you can build up a galaxy of millions and many millions of cells. And the advantage of doing this is that you don't need, I mean, it takes some memory in the computer for each of these cells. But if you don't have, like say here in this corner, the density is very low, then you don't need to have the same resolution as you do here. So that's why it's very, very good to use this approach, this so-called adaptive mesh. So it's a mesh of cells that are refined adaptively. This approach may be interesting for some of you that are studying to become like real physicists or engineers. It's used very much in all sorts of hydrodynamics. So, for instance, here you see the airfoil of the wing of a plane. And if you want to simulate wind coming across this wing, then you can use the same approach where you simulate how the gas moves in these cells. It's also used in, for instance, calculations of windmills, or maybe also in explosions. And in here it's you see how the water that is flowing behind some, let's say, a pillar acts. So this could, for instance, be a windmill in the ocean, and then if you want to simulate how does the water flow around, if you want to be sure that you don't erode the bottom of the sea, for instance, you can use this approach, adaptive mesh refinement, or AMR. Another way to simulate how gas flows is called SPH, smooth particle hydrodynamics, and maybe that's a little easier to understand conceptually. So here you follow particles around. In the other approach, you had cells that were static, and then you calculated the flow of gas through the cells. In this approach, you follow particles around. And this corresponds to basically atoms, but each of these particles then represents a much larger chunk of gas than just one atom. So, for instance, from a simulation of galaxies, this could represent 10 to the 4 or 10 to the 5 or 10 to the 6 solar masses. But then the thing is that each particle is not just the particle. You think of the particles as smoothed over space. So if I want to calculate the density here, I take a weighted average of all the neighboring cells. So you see this particle contributes mostly, and then number 3 contributes a little less, and number 6 even less, and maybe this one doesn't contribute at all. So the exact shape of this smoothness is called the kernel of the particles, and there are various mathematical forms to represent these particles. So that's another approach. and these are the two like main approaches to simulate the flow of gas or water, like fluids. You can also actually have a hybrid model where you have particles that move around, but each particle also has a cell that, like in the AMR approach, but the cells are not necessarily square or cubic. They can have any shape. So this is called moving. So the mesh itself moves. So it's called moving mesh. And here's I found this simulation. So you have the mesh here. They are triangulars, but and it's a 2D simulation. But in 3D they can have any shape you want, and this sort of mixes the best of two worlds. So each of these methods have both pros and cons. So here I want to show you such a simulation made with the moving mesh simulation. It's called Illustris, and here you have billions of particles, and each particle is surrounded by a cell, and then you calculate the density and temperature, and also sometimes a star forms when the gas is dense enough, and then it explodes and it produces heavier metals. So the metallicity in each cell is also calculated. And then you see, you start 400 million years after the Big Bang, and then already half a million years later, the gas has condensed into clumps, and these clumps will then become galaxies. Here in the beginning, what you see is only the color just shows you the mass density. So you have very dense clumps sometimes, and then you have huge voids where the density is very low. And then around now, the color scale changes to show the metallicity, I think. Just a second. Now we are a few billion years after the Big Bang, and you see galaxies have formed in all these clumps. And they're not dispersed completely at random, but lie along these filaments. Now you see stars are forming in large amounts, and these stars explode and push gas out between the galaxies. As you see these clouds that are like of gas that is exploding. So here you have, this is called a cosmological simulation. You have thousands and thousands of galaxies. Each of these galaxies then consists of thousands of particles. And if you want to know about galaxies, you can take one of these. Let's say you want to know about galaxies at when the universe was 1 billion year old. Then you stop the simulation at 1 billion years, and you zoom in on one of these galaxies. You can even re-simulate a galaxy as it is at higher resolution. So for a given computer power, you only have you can only do a resolution up to some point. But then if you want better resolution, you can re-simulate, zoom in on one region, and then use more particles to that particular region. So this is how we can simulate the galaxies. And then we can take one galaxy and put in such a grid that I showed you before, and then perform this Lyman alpha radiative transfer. So in this way, we can simulate how galaxies look if we look at them through a filter that filters only the Lyman alpha. So this is from such a simulation. This is a galaxy at it's around, let me see, 1.5 billion years after the Big Bang. You see, this is the same galaxy seen from two different directions. And you see that here it's lying along a filament. You see, here is gas here, but not here and here. But if you look at it from this direction, then it's more spread out. And then so this is how it would look if the Lyman alpha were able to escape directly. But as I've been explaining, it is not. It will scatter on all the neutral hydrogen that is in the galaxy and around the galaxy. And so when we look at it in reality, it will look like this. So what happens is that the Lyman alpha photons are spread out over a much larger area. So the galaxies actually look much larger when we look at them in Lyman alpha than if we look at it in some other wavelength. And we did some simulations that actually confirmed very nicely how the observations of such galaxies look. What you also see is that the same galaxy can look much brighter when observed from one direction than when observed from another direction. Lyman alpha is scatters, and it will tend to take the easy way out. So if you have an anisotropic configuration of gas, so more gas in one direction than in another, then the Lyman alpha will it will prefer the easy way out and take the path where there's less gas. So in this case, there's a lot of gas here and not so much gas here, so it looks much brighter. This is a problem because usually if you want to know, so one thing that we always want to know about galaxies is how many stars does it produce, the star formation rate. It's measured in solar masses per year. And so the way to do this is, one of the ways is to see how much light do we have from the galaxy. But in this case, we don't know when we observe a galaxy. I mean, we can only observe it from one direction, and we don't know if we have observed it from a direction with a lot of gas or a direction with a less amount of gas. So one of the ways that people calculate the star formation rate is from Lyman alpha, but it's actually not a very good way. Also because Lyman alpha is more prone to be absorbed by dust than normal light. So let me just check. Yes, okay, almost done, I think. So in this way, we can predict how galaxies look in Lyman alpha. We can also go the other way and take the more simple model of a galaxy that doesn't look like a real galaxy, but we can let's say a galaxy is described by just a few numbers, namely the density of gas, a shell of gas that is expanding, corresponding to gas that is being thrown out of the galaxy. Here is a spectrum of a Lyman alpha emitting galaxy, and you see, as I talked about before, one peak is suppressed, the blue peak, and the red peak is enhanced. So this is because there's outflowing gas. So we can calculate in this simple model the spectrum of a galaxy with some density and some outflow velocity, like in here. And then we can do it with a number of galaxies with different densities, and we can give these galaxies different outflow velocities, so we can create such a grid with many simulations of gas outflowing from Lyman alpha escaping from gas with different densities and different outflow velocities. So here you have a grid of velocities and column densities. And then we can calculate the spectrum in all these cases and compare to an observed spectrum. And here the shape tells you how good fit it is. And you see here is the best fit. And the spectrum of that particular simulation looks like this, the red one here over here. And that has an outflowing velocity of, in this case, 160 kilometers per second, and a certain amount of neutral hydrogen, so column density. And then you can look at the other simulations that have almost as good fit and have some uncertainty. Sorry. Yeah. So here you see the spectrum. The best fit spectrum is the red line, and the shaded area here is the spectrum of all the models that gave a fit that is within 1 sigma of the observed. So this gives you a constraint on the uncertainty. So in this way we can use a simple model, but where we can tune the parameters and then get an idea of what is it we're looking at. Even if we don't see the galaxy, we only see the spectrum. So I'm almost done. This model that I just talked about is very simple. In particular, it assumes that the gas is homogeneous, but we can go further and then introduce some clumpiness in the gas by representing the gas as spheres with some density, and so you have higher density, and then between these clumps you have lower density, and these clouds can move out of the galaxy and they can move around. But you soon get very many parameters. And so before I showed you a grid of 2 parameters. If you have 11 parameters, you have an 11-dimensional parameter space, then you really have to do a lot of calculations. And each calculation can take several hours. So it soon becomes infeasible. But this is a better representation of a galaxy. You have galaxies that very often look like this. You have some disk, and then you have gas being thrown out of the perpendicular to the disk of the galaxy. So the last minute, I will just show you some very latest result on the if there are. Oh yeah, I've just been babbling about Lyman alpha. So my conclusions is basically just that I like Lyman alpha, and we can learn a lot about galaxies, but it's also quite difficult to interpret. Yeah, thanks for your time, and if you have questions, you're very welcome. I think you're muted though, but
Switch up.
Yeah.
Okay, so thank you so much. I hope you heard the applause. But we have some questions here. So I don't know if someone from the public has some question. Okay, I do have a question for you. I feel that what you explained, this phenomenon works in hydrogen atoms. That, like, when you showed the animation, it was for hydrogen atoms, but does it work? Does that happen for like all types of atoms, or why is just hydrogen that? Is it just hydrogen, or how does that work?
Yeah, thanks. That's a good question. I mean, so this is this happens in principle for all atoms, but 9 out of 10 atoms in the universe is hydrogen, and most of the rest is helium. So helium has the same, but it's another. It's because helium, the energy difference between the ground state and the first excited state in helium is a higher energy, so you need more energetic photons. And then because the density of the helium is lower because there are just fewer helium atoms, then first of all you need very high energy photons, and you don't have that often. And second, there's less helium, so it escapes more easily, so it doesn't scatter that much. But in principle, you're right, you do have it for helium, and you also have it for all the other atoms, but the other atoms are so few in number. I mean, so there is a reason that for an astronomer we only divide the universe in hydrogen, helium, and metals. Everything else we call metals, because for us there is almost none of the rest. So in principle any atom, but in practice it's only hydrogen.
Thank you. Is there other questions here? Sure.
But yeah, so I these computational methods that I talked about, they're very efficient, not only for galaxy formation, but also I showed you these examples of the windmills and all this. So if you want to be a physicist or an engineer, this is something really, I mean, not only for astronomers to look into if you want to be like a theoretical physicist or so. But the Lyman alpha is probably only interesting to astronomers, but I'm hoping that I could interest you anyway in it.
Well, I think here we have one question from the transmission. So Claudia Porno asks, with the Lyman alpha, can we study and confirm if the galaxies that are found with the James Webb Space Telescope
sorry, Pablo, you fell out for a second, so I didn't get the beginning of the question. Can you try again?
Okay, wait. So Claudia Porno asks, with the Lyman alpha, can we study and confirm if the galaxies that are found with the James Webb telescope that are found in 300 and 400 million years after Big Bang are really galaxies?
So the question, as I understood, is about the galaxies found with the James Webb telescope 300 or 400 million years after the Big Bang, and whether we can. So I didn't get the very last three words. I think if you can study them.
I'm not sure. I think she hasn't sent the full question because I think it's incomplete.
Okay, but if I understand correctly, the question is about observing Lyman alpha from the very early galaxies with James Webb. And this is indeed something we do. So because Lyman alpha is emitted, especially when we are forming stars and galaxies. So galaxies that are in the beginning to form, they form a lot of stars, and then they become very prominent in Lyman alpha. There is a problem, though. The problem is that in the early universe, 300 or 400 mega years after the Big Bang, the universe, the gas between the galaxies was neutral. So that means that even if the Lyman alpha is able to escape the galaxy, it still has to propagate through the intergalactic gas. And that is actually a problem. So usually when you see a spectrum of a galaxy at this age, you have a continuum of light of up to Lyman alpha, and then it drops sharply. So for these early galaxies, we don't see Lyman alpha in emission, but we can often see a Lyman alpha break. So if we measure where is the break, then we know this is where Lyman alpha is supposed to be. And then the problem is that the exact wavelength is very dependent on how much gas there is. If there's a lot of gas, then the break is pushed a bit further to the right. And if there's less gas, or even sometimes you can have ionized bubbles around the galaxies, and then it's easier for the Lyman alpha to escape. But so in conclusion, Lyman alpha is definitely used to look for these very, very early galaxies, but it's even more difficult to interpret at these high redshifts galaxies. I hope that was.
No. Question for Peter? Okay, I think that's it. Thank you very much for your great speech. I think it was very instructive and it was very interesting to learn a little bit about this Lyman alpha radiation. So please, another round of applause for Chris.
Thank you very much. Thank you. And can I just ask? I mean, I've been writing with Pedro, but you're not Pedro, right? You're Pablo.
Pedro is my friend. Pedro is.
Okay. Yeah. Okay. Yes. Okay, good. So say hi to Pedro from me, and yes. And thanks again for your time.
Yeah, thank you for your time. Thank you very much. And we're going to be sending you a certificate for our participation, like as an acknowledgement. So thank you very much. And to everyone else, we're going to continue, maybe have a less than 5 minutes break for to continue with the next speech. Para hablar. Bueno, tenemos un breve